All right, so good morning, everybody. Hope you're doing well. So my presentation today is focused on the prediction of the seismic compression of unsaturated backfills. This is a topic that I've been working on with my students for maybe 12 years or so. I started at University of Colorado looking at some centrifuge tests where we were trying to measure the seismic compression of sand layers having different uniform degrees of saturation. We developed a empirical methodology to try to predict that. We just finished a series of tests that were performed by my previous PhD student. It's not going forward. 1 second. Wenyang Rong. And he performed a series of cyclic simple shear tests that I'll show some of the results today. He was originally going to work on this project, but at the middle of the pandemic, he got a job offer from McDonald's, so he's working there in San Francisco. So it took a little bit of time to recruit a student to work on this project, but Del Canicolas is a master's student at UCSD. She started working on this project this summer. So she's getting up to speed, and we're working on basically creating an effective stress-based constitutive model for unsaturated soils where we're able to predict the evolution of seismic compression. And our goal at the end of the day is to try to integrate this into OpenSeas. The presentation today, I'll give you a quick motivation for why we want to study this topic, give a brief overview of some of the different issues that we need to address when we're trying to develop a model, the effective stress state, how the effective unsaturated conditions affect the dynamic soil properties, and then also some of the different mechanisms of seismic compression and how people in the past have tried to develop empirical methodologies. Then I'll go over the objectives of this particular peer project, show some of the key features that we observed from our cyclic simple shear tests, and then I'll start to show some of the progress on the development of an elastoplastic constitutive model for the seismic compression. We're basically extending the UBC sand model to unsaturated conditions, and we're adding some hydraulic coupling features into that. So people are maybe perhaps aware of what seismic compression is. It's the accrual of contractive volumetric strains in soils due to cyclic shearing. It's been recognized as a major cause of seismically induced damage to buildings and other transportation infrastructure in some of the past earthquakes in California. It may be something that we need to consider in site response or serviceability analyses. There are some empirical approaches that I've mentioned before where you can estimate the total amount of seismic compression that you're going to obtain at a site, but we don't yet have a physics-based methodology that will help you understand the evolution of the seismic compression and all of the main variables that are controlling it. These are just some of the typical results from the centrifuge tests that I mentioned before. Seismic compression is, you could look at this from a dry soil side, a saturated soil, or an unsaturated soil perspective. From the dry soil side of things, you're just basically collapsing the dry soil and collapsing the voids. From the saturated perspective, you're going to be building up pore pressures, potentially liquefying the soil. Those pore pressures are going to drain after the earthquake event, and there could be some settlement. But for the unsaturated conditions, it's going to be a mix of both of those mechanisms. And then we have the additional contributions of suction to the effective stress state that could provide some resistance. And in this study by my previous student, Majid Qayumi, he observed that for some middle range of degree of saturation, he was seeing the lowest amount of seismic settlement. So why is this important in transportation structures? We tried to build a lot of the above ground geotechnical structures that are supporting transportation infrastructure to be unsaturated. So these unsaturated backfills are used in mechanically stabilized earth walls, MSE bridge abutments, which is a new popular area. And then also embankments for roads and rails. This could be an important design feature because even a small amount of settlement that occurs in these backfills could have a major effect on the superstructure, especially when you're looking at a MSE bridge abutment. And while looser soils are probably going to be the more important material that is going to show more seismic compression, dense backfill soils that are compacted still do show some contractile strains during cyclic shearing. And usually when you get closer to the face of a retaining wall, the density could be lower, and that's where deformations are critical to understand. I just showed this to think a little bit about the degree of saturation variation with depth. It could be very complicated in a site depending on the depth of the water table and the infiltration and evaporation conditions. The condition that we're going to be focusing on in this study is where the degree of saturation is uniform with depth, the water content or the suction. And we could say that that's representative of a compacted soil structure. One of the key variables that we're going to be using in our constitutive model is the saltwater retention curve. In this relationship, this is quantifying the amount of water in the soil for the amount of energy that it takes to withdraw the soil. In this capillary regime, the soil is still close to saturated. In the pendular regime, your soil is pretty much dry. So we're really going to be focusing on this funicular regime where there's a large amount of changes in degree of saturation with changes in suction. We need to think very carefully about hydraulic hysteresis, which means different paths of wetting and drying that are going to happen. And usually in some experiments that we've already performed, we've seen that if you're starting on a drying curve, the seismic compression process is going to lead to a wetting scanning path. The soil retention curve is important because it's linked with the effective stress in soils. Effective stress was proposed, the concept was proposed back in the 1950s by a bishop, but in the last decade and a half, Ning Liu has done a lot of work to try to simplify this approach by coming up with a suction stress concept. And if you make some key assumptions on the suction stress, you're able to integrate this soil retention curve equation down here into the effective stress equation and show how this suction stress parameter is going to vary with the degree of saturation. So we're going to be focusing on the sandy type materials that have a suction stress characteristic curve that will increase and decrease. So if you're at some middle range of degree of saturation, you're going to be having the greatest increase in interparticle forces in your soil. And those are going to be potentially restraining the amount of seismic compression that you're going to see. It's very complicated when you're trying to think about effective stress and soil compression, because usually you think that we define effective stress so that everything is related on a one-to-one basis for it. So if you have an increase in effective stress, we do expect to have a proportional increase in the elastic volume change through Hooke's law, which means that any changes in suction degree of saturation or net stress are going to lead to elastic volume changes. The effective stress is also going to affect our shear and bulk moduli. But one of the things that's going to happen when you have collapse phenomena, either due to collapse upon wetting or due to seismic compression, that's an elastoplastic concept. So having knowledge of the effective stress change is not sufficient. We need to have an elastoplastic model to tell us what's happening. We also have to keep aware of the drainage conditions in unsaturated soils. Usually when we're looking at liquefaction, we're having only water inside of the soil and you're not allowing any drainage to happen. So there's not going to be any volume change during the shaking event, but the pore pressure is going to increase. So in unsaturated soils, you could have drain conditions if the shearing is slow, some partial drainage conditions, or fully undrained air and water phases, which is what we're going to be focusing on in this study. And in that case, we're going to have changes in both air pressure and water pressure. And the difference between those is going to affect the suction. So some of the challenges that we need to think about are that the voids that are filled with air are going to collapse and densify. Both of the pore fluids, the air and water, are going to pressurize. The differential pressurization of those two phases is going to lead to changes in suction. As the voids filled with air start to collapse, then our degree of saturation is also going to increase, because the degree of saturation is the volume of water divided by the volume of voids. And if the voids are getting smaller, the degree of saturation increases. So when you combine the degree of saturation together with the suction to obtain the effective stress, you can see that it's a highly coupled process. And then those changes in effective stress are going to change our moduli, which could, on the next cycle, start to affect our predicted changes in all of the other variables. This is just showing some typical trends that have been measured in the past on showing how the elastic properties, the shear modulus, are related to the effective stress in unsaturated soils. These are for different sands. And also the damping. There hasn't been a lot of study on this, but we know that as the degree of saturation increases, there's a decreasing trend in the damping ratio. So the past work that has been developed on this topic for the methodologies has been primarily empirical. My previous student, Majid, who's now a professor in University of New Hampshire, developed an empirical model where he combined the relationships from Tokimatsu and seed for dry soil collapse and the consolidation due to dissipation of excess pore pressure from Ishihara and Yoshimine into a single equation, and had some linkages with the degree of saturation on top of that, and basically added those two mechanisms of seismic compression to come up with your overall seismic compression. This model works. It gives you a total amount of volumetric strain in a soil layer for a given shaking event. However, you can really get whatever relationship you want, depending on the parameters that you choose. So you can have choices of different of the components in the model, and it's going to change the shape of that U-shaped relationship that I showed before. Further, it's not very simple in this empirical model to tell us the evolution in the seismic compression with the number of cycles. So getting on to the objectives, we're trying to develop a new effective stress-based elastoplastic model. We want to depart from these semi-empirical approaches so that we can try to capture the effect of unsaturated conditions on the deformation. We want to build upon an established but simplified model so that it's going to have a practical, a good effect on practice. So we want it to be able to be used readily in practice. So we wanted to take a simplified model and expand that to unsaturated conditions. We want to add a pore mechanics approach to better consider the generation of pore air and water pressures. We want to look at changes in the effective soil retention curve, and also look at how the soil dynamic properties are going to evolve as the effective stress changes. And then we're going to use some results from some simple shear tests to calibrate and validate the model. So just quickly, I'll browse through some of the previous work on the experiments that we performed. We did some cyclic simple shear tests on a suction controlled device. We were able to measure independently the changes in suction and the changes in their pore water pressure and pore air pressure during cyclic shearing. We tested mainly well-graded sand, which could be used as a backfill material in transportation structures, and performed some drained and undrained tests. I'll just show some typical undrained results here. We did some strain controlled tests. So we measured the changes in shear stress. We did see the change in volumetric strain. This is for a specimen with initial degree of saturation of 0.3. So there's a pretty good amount of air in the soil. So there's volumetric strains that happen due to that. We measured the changes in pore air pressure, pore water pressure, and pore air pressure. And the difference between those is our matrix suction. So even though both the pore air and water pressures increased, the differences indicate that the matrix suction decreased. So that could affect our hardening process that's happening on the yield surface. And also because the we observed an increase in the degree of saturation because of that decrease in the volumetric strain. So when we combine the degree of saturation together with the matrix suction, we find that the mean effective stress decreases. So that means that our shear modulus is also going to be getting smaller. So we repeated this for several different initial degrees of saturation and came up with some cyclic trends and integrated it, and we found kind of a smile shape similar to what was observed in the study by Gayumi. And this nonlinear response here was due to the fact that we did fully undrained tests. In Gayumi, it was a partially drained centrifuge test. We did some comparisons with drained tests, and because of the decrease in the effective stress, the undrained soil, undrained conditions lead to more volumetric strain. So you can see that there's a large decrease in effective stress in the undrained tests, and that leads to a softening of this small strain shear modulus.
John, sorry to interrupt. You're at your time. If you're able to reach conclusions.
So these slides I wanted to just leave in case we had discussion on the model, but we've developed some hydromechanic coupling, some different relationships that we're putting into UBC sand. And we're using some methods to predict the evolution of the air pressure and water pressure during cyclic shearing. And you can see that there's a large amount of coupling. There's a lot of things that affect other things. We have gotten some preliminary results that look similar to those experimental results I was just showing. But these are performed in FLAC and they're not very transparent. So the approach we're using now is to look at cycle by cycle analysis. So we're trying to go through this flow chart to really explain how everything is happening, and then we can use our observations there to refine the pore mechanics that we're using to predict our pore air and water pressures during each cycle. So yeah, sorry to go over a little bit, but I think this effective stress based approach is going to have some potential to help us understand the evolution of seismic compression during earthquakes. And Dell has a lot of interesting but hard work to do through the rest of this project. So thank you very much.